Okay, well, thank you very much. First of all, I should say many of the things that we will be doing are sort of slightly dangerous, okay, and sort of singed a few hairs every now and then. Please do not try and replicate anything you see here at home. Okay, I say it's very easy for these things to get out of control, and each time they may just occur slightly differently, and you may think you know what you're doing, and something else happens. So please do not try to replicate anything. Okay, right, now then, with that, we shall start. And the lecture is all about fire and flame and combustion. And so, well, here's a simple fire. These matches are burning quite nicely here. But what exactly is this? What does it mean? What is combustion? So this is a chemical reaction that's taking place between the wood here and using up the oxygen from the air. And a chemical reaction is taking place with the liberation of heat and light energy. Now then, goggles on. Plenty of things burn, and in these trays here I have some alcohol. And let's see if we can set fire to that. Can we have the lights down, please? Okay, so say the trays contain an alcohol, and this is burning with the evolution of heat and light. And we've added some metals to the trays here to give the different colours to the flames. So we have some strontium added to the red flame there. The yellow flame contains sodium ions. And this one over here contains boron, which gives the beautiful colour. And these, of course, are very important in fireworks. All the colours that you see in the flames there are also due to the metal ions that are added. Okay, right. Have the lights back up, thank you. So many things burn. Have some cotton wool here. Not terribly exciting, but it does easily catch fire. Doesn't burn really well. It burns quite slowly. It's not burning completely. It'll leave some black residue of unburnt carbon here. So it's quite difficult to get it to burn well, but we'll see if we can improve that later in the course of the lecture. So cotton wool doesn't burn quite so well. Many things burn, and if we have them in a very finely divided state, you can get some very unexpected reactions with things burning. Okay, now for this one is just a tad frisky. So I need to be properly protected for this. Right. So I'm going to burn something particularly flammable now, and this is flour. Okay? Right. If we have the lights down again, please. Thank you. Okay. Don't try that at home. Thank you. Okay. So, actually, it's a very serious matter that flour mills need to be very careful because they can explode if they get a very fine mixture of the flour and air. This has been known to destroy entire flour mills. So, even sort of things that you wouldn't really expect to burn can burn. All of these things that we've seen so far, the wood from the matches, the flour, the cotton, they're all examples of carbohydrates. Now, these are substances that contain carbon, hydrogen, and oxygen, and the carbon and hydrogen burn, and we end up with, so this is the reaction with the oxygen in the air, and we form carbon dioxide, gas, and water, or hydrogen oxide. Okay, so now remember the cotton wool didn't really burn terribly well, but we can improve things if we add a little bit more oxygen. So the cotton wool initially was just burning in the air, using the oxygen from the air. If we add some more oxygen to this, so this is now concentrated oxygen in the form of liquid oxygen, we should be able to get it to burn a little bit more vigorously. So I'm just pouring on some concentrated oxygen, liquid oxygen, And we'll apply light to this and see if it burns slightly more quickly. Okay, so a little bit of oxygen helps enormously. Carbohydrates, such as the cotton there and the wood and so on, burn in oxygen, but carbohydrates also, it's the burning of carbohydrates that give us our energy from our food. Now I have some carbohydrates here. This is a chocolate chip muffin. Okay, so not only does it contain carbohydrates from the flour and sugar, it also contains fats. All of these burn, and actually this is what gives us our energy. It's the reaction of the food with the oxygen that we breathe in. So I'm going to add some concentrated oxygen again. Actually, we'll have a little screen at the back here, I think. Right, so we'll add some concentrated oxygen to the chocolate chip muffin. Thank you. And then apply a light. So you should be able to see some energy being released. Okay, now it says on the back of the packet the muffins came in that they have around 500 calories in each one. Okay, so this energy is what we're seeing being released here. Okay, these 500 calories are the energy that we get from our food, the reaction with the food as it slowly burns, not quite like that in our stomachs, but releasing the energy nonetheless. Okay. Now, many things burn, even metal can burn. So I have here some steel wool. This is the sort of thing, well, it's made of iron, and it's the sort of thing that you might use to clean your pans in the kitchen. And even this can burn. So we're going to give this some oxygen, some more concentrated oxygen, liquid oxygen. And if we just have the lights down in a second. So this is iron reacting, oh dear, reacting with oxygen, if my candle can stay alight. There we are. Okay, so there we are. Even the iron can burn by combining with the oxygen from the air. But what exactly happens when things burn? Obviously, a lot of energy is given out, and heat and light and so on. But where do things go? So these candles here, when they're burning in the air, well, what happens? We see the light and heat is given out, but eventually they disappear. There's nothing left. Well, the candles are made of solids called hydrocarbons. Hydrocarbons are substances that contain carbon and hydrogen only, and petrol is an example of a hydrocarbon. It's a liquid hydrocarbon. We also see gas hydrocarbons as well, and we'll see some of these later, but this is a solid. But nonetheless, when these burn, they combine with the oxygen, and what we end up with is carbon dioxide gas and water. Now, we can show this using the apparatus here. What we're going to do in a minute is draw the gases that are being given out as the candles burn through the funnel, and we have a test tube here that's been cooled. So this is being cooled down so we can condense any water vapor that might be given out. And the solution in this flask here is called lime water. And this reacts with carbon dioxide gas. And in the presence of carbon dioxide, a white, milky-coloured precipitate forms. So we need to keep an eye on this when I put the candles on there to see if we can see it changing from the clear colourless solution there to a sort of milky white solid forming. So put the candles in here. The gases are being drawn through the apparatus, and already you can see the lime water beginning to change. It's beginning to go milky now. This is the formation of, well, it's essentially chalk, giving us a white precipitate in this. So this is the carbon dioxide that's being given out as the hydrocarbons are burning. So the carbon in them is forming carbon dioxide. And if we look in the test tube, we might be able to see a few drops of water beginning to form. In fact, we can see there's a few drops in here and in the tube at the top and a little drop about to drip down, I think, into the bottom there. So water vapor is also being produced during this combustion. But what about the metal? What happens to that when it burns? Well, again, it's combining with the oxygen from the air, forming iron oxides. And we can show this on the balance in the front here. So I have some iron wool on the balance. We'll just set this to 0. And in a moment, we're going to start this burning, combining with the oxygen from the air. And hopefully, you might see a change in the readout on the balance. So if I just start this, get this to burn. Now, it's not quite as vigorous with the oxygen that I added before. That was concentrated oxygen. This is just going to burn in the oxygen from the air. It's much more slow and controlled combustion. We have the lights down, please, just to... There we are. It's just going now. So let's start it around here as well. So it's slowly burning, and the reading on the balance hasn't yet gone up. I'm hoping it will any moment. That's it. All right, and now it's going up. That's it. Phew. Okay, so what's happening here? The iron wool is combining with the oxygen from the air, and a chemical reaction is taking place that's giving out heat and light. And, well, the reading here is increasing. It's getting heavier. So the iron is combining with the oxygen from the air, forming iron oxides, and it's trapping the oxygen from the air in this new chemical compound, and the chemical compounds that are being formed, the iron oxides. So now this is a gram heavier than it started off. This is because of the air trapped in this, the oxygen chemically combined with the iron. It's 1.2 grams heavier, still increasing as it's continuing to burn. Okay, so we can show this using a chemical equation. If we have the slides on, please. The iron is combining with the oxygen from the air, forming, well, various iron oxides here, and releasing energy in the form of light and heat. Okay. Well, some other metals are even more reactive than the iron that we saw, and one of these is magnesium. Magnesium is just a silvery metal. This is in the form of magnesium ribbon here, and this burns in air very easily and gives out a lot of energy in the form of light and heat, but a brilliant white light. So you can see this here. We have the lights down, please. So a brilliant white light as the magnesium reacts with the oxygen from the air. And if we have the lights back up for a moment, please, well, you can see the smoke that's being formed here. This is magnesium oxide that's formed during this chemical reaction as the magnesium combines with the oxygen from the air. And if we manage to trap all of this smoke and the ash that's left here, we would see that that would also be heavier than the metal itself, than the pure magnesium. This is as the magnesium combines with the oxygen. So the chemical equation for this is magnesium reacting with oxygen to form magnesium oxide, and again, releasing a lot of energy in the form of heat and light. Well, in each case so far, then, we've seen various things burning by combining with the oxygen from the air. Oxygen is really reactive. We've seen it reacting with magnesium, with iron, with the flour, with muffins, all sorts of different things. Well, let's have a look at some oxygen now. Oxygen itself is a gas. It makes up around 20% of the air that we breathe in. And Chris here has filled this balloon with pure oxygen gas. Okay. So the balloon contains pure oxygen, and what we're going to do is light this, okay? So pure oxygen, really reactive, all sorts of things burn, you've seen burning with pure oxygen. So this is pure oxygen itself, and I'm going to light this. Are you ready? Okay, well, that was a bit rubbish, really, wasn't it? Okay. In fact, all that happened there was the balloon just burst. Oxygen itself does not burn. Okay, so oxygen doesn't burn. It needs something to combine with. You've seen things burning in oxygen. In fact, if I tried to light a jet of pure oxygen, well, we'll see it wouldn't burn at all. Let's try it. Now, we have over here a special gun that will come in very handy later. And when I pull the trigger here, gas comes out. It's pure oxygen gas, and I'm going to see if I can light it. So let's try and light it with a candle. Well, it certainly doesn't light, but what it should be able to do is help the candle burn a bit more brightly. So the oxygen itself is not catching fire, but it does enable the candle to burn more brightly. So the candle is burning, the fats from the candle burns in the oxygen here. So oxygen itself is not flammable. Okay, but there are other gases that are flammable, and I have a couple of balloons out here with two different gases in them. So. Right, I have two balloons here. They both look just the same. One of these is filled with air, and one of them is filled with hydrogen. Now, which one's which? How can we tell? How can we tell? Let go. Let go. Ah, you're guessing. Ah, but you say let go. Let's try that. Let's let go then. Ah, now, can you guess which one's got the hydrogen in? Yes, this is the hydrogen, and this balloon is filled with air. Now, so the air sinks. Well, this is actually because the air that's inside here is the same density as the air in the rest of the room, of course, but the balloon is heavier, and this is why this thing sinks. This gas is hydrogen, and hydrogen is lighter than air, which is why it goes up. Now, the balloons that you normally get that go up are not filled with hydrogen. They're filled with helium, that's right. We don't use hydrogen because hydrogen, well, as we shall see in a moment, is very flammable. Helium isn't flammable, but hydrogen is. I'm just going to put this one out the way. I'll put this up here to keep it safe in this tube. There we are. So that floats up nicely and just fits. That's handy. Almost as if we'd made it fit. Right. Okay, now we're going to have a look at some hydrogen. So hydrogen burns. So Sarah here has another balloon filled up with hydrogen gas. And we'll see if we can light this one then. So remember, the oxygen did not burn at all. The balloon basically just burst. Let's see what happens with hydrogen. Okay, are you ready? So remember what happened to the oxygen. The balloon just burst. What happens here? Oh, well, that's a bit more interesting. Well, in case you missed that one, we've got a few more for you. Okay, thank you. All right, okay, so let's see what happens with this lot. Right. Okay, so I hope you agree then that hydrogen is slightly different from the oxygen. Hydrogen does indeed burn. Now, in one of my sort of slightly daft moments, I thought, well, I know what would be a really good experiment. We should try and strike a match inside a really big balloon of hydrogen. That would be good. Okay. My technicians don't agree with me on this one. They think it's a really stupid thing to do, and they get very nervous every time. But let's give this a go. So in the bag here, well, we've filled it up with hydrogen gas. All right, just to be safe here. Right. So I'm going to strike a match inside, if I can get my hands in here, inside this glove bag. Sorry, can you give me another hand, please? Thank you. It occurred to me the other day when I was doing this, I should have been a vet. But anyway, right. Okay. Now, I have a match, and I'm about to strike the match inside this big bag of hydrogen. So watch carefully what happens. Aha. So the matches do light, and this is because the matches contain all the oxygen they need built into them, but, phew, I always get slightly nervous, but the hydrogen doesn't light, and I think I'll quit while I'm ahead there. And we'll just prove that it really is hydrogen in here. So Mark is going to squeeze out some of this hydrogen through this jet here. And I should be able to light it just to show that it really is hydrogen. So there we are. Burns with an almost colourless flame, but I can easily relight my match in it. There we are, just to show that it really is hydrogen gas that was inside the balloon. Good. Phew, that's over. Now, why doesn't it burn? Why doesn't it burn? Because there's no oxygen, there's no air in there. All there is just hydrogen. Okay, now then. So I thought, yes, that's okay. Where can we go from here? Well, just going to bring this out to the front so you can see it more clearly. Remember, the hydrogen balloon was in here, and the hydrogen balloon is floating merrily in the air. Now, I can make this balloon go down by magic. Watch this. Zzz. See, watch this. It's going down any second. Oh, there we are. Look at that. See, magic. So why is this going down now? Well, remember, hydrogen floats in air, but the air balloon didn't float in air because the balloon itself was slightly heavier. Well, what we've done now is fill this tube up with hydrogen gas, and so the balloon no longer floats inside it because the balloon itself is heavier. So hydrogen doesn't float in hydrogen, just like an air-filled balloon doesn't float in air. So this tube now contains hydrogen. Now, remember my oxygen gun? And remember how we couldn't light the oxygen gas? Well, we can't light oxygen in the air because oxygen doesn't burn in air, but can I light it inside the hydrogen? Right, this is slightly nerve-wracking. Okay, now there's a little electrical spark on the end of this, so when we're in place, Mark, not before, we can start this sparking, and we're going to let the oxygen come out, and it should light inside the hydrogen here. Okay, so remember, oxygen doesn't light normally. So ready? Need to check here. It's and fireman Nick is on. Yes, good, thank you. Right, okay. So, okay, we're in. Sparker on, and oxygen, and there we are. So this is oxygen gas burning in hydrogen, which is actually pretty good, really. So oxygen itself doesn't burn in air, but it does burn in hydrogen. Okay, off. Right, now, phew, so far so good. Well, I thought, okay, so we can light oxygen inside hydrogen, but could we set fire to a piece of paper soaked in petrol in hydrogen? Right, well, let's give that a try. Yeah, yeah. So here's some paper, just to show, soaked in petrol, burns very nicely. Right, oh, I just need to lower the little clamp that we have. Okay, so piece of paper soaked in petrol, clamp it in place, raise it up. There we are. Right, now then, what will happen? So, ready? Okay, click it on. Okay, so the oxygen is now burning, and the petrol and the paper do not burn. Only when the oxygen flame is directly on this does the paper begin to smoulder, but it certainly isn't catching fire. Okay, off. Right, thank you. Right. Phew, that's good. Now, remember the balloon filled with oxygen, and it didn't light in air. Will it light in hydrogen? Well, let's give it a try. So we have here a little tiny balloon filled with oxygen. And we're going to see if we can set fire to this. So a little tiny balloon, and we're going to set fire to this in hydrogen. So this is a balloon of oxygen. Right. Okay? Ready? Good. Okay, so off. Clicker on. There we are, fantastic. It instantly burst, maybe a bit too quickly, in fact, but never mind. Right, off. Okay, good. Phew, marvelous. Thank you. So, oxygen doesn't burn in air. Hydrogen doesn't burn without any oxygen. It's the two together. So just imagine if we were on a planet made up of hydrogen gas. Well, it wouldn't burn. We wouldn't think that hydrogen was very exciting. We'd say, well, hydrogen, that doesn't burn. Could we find such a planet, though? Well, here's a planet. Anyone know what planet this is? It's Jupiter. That's very good. You're very good with your planets. Yes, this is Jupiter. So if we were standing on the surface of Jupiter, well, actually, that would be slightly hard because Jupiter is actually a gas giant. It's just made up of gases, and the main gas it's made up of is hydrogen. So we couldn't really stand on the surface because there isn't one. But if we were at Jupiter and we had a balloon filled with hydrogen, it wouldn't burn at all. We'd say, oh, hydrogen, that's not very exciting. But if we had a balloon of oxygen, well, we'd say that the oxygen was very flammable, and we'd need to be very careful with the oxygen balloon. Okay, right. So we've seen hydrogen burning in oxygen and oxygen burning in hydrogen, but they've been burning with a nice, quiet, gentle flame. What if we want to get a bit of a bang out of this? Well, we can do this. We need to mix up the hydrogen and the oxygen in just the right ratio. So Sarah here has filled up a balloon with hydrogen and oxygen gases all mixed together. And this particular balloon has equal amounts of hydrogen and oxygen. Right. So this one should go with a little bit of a bang now. Now, we've seen the hydrogen balloons before. They went with a sort of a bit of woof. These ones are going to go more with a bang. So if you don't like bangs, do put your fingers in your ears. So this balloon contains equal amounts of hydrogen and oxygen. Okay, are you ready? Well, that was certainly... So that was certainly a bit louder, but we can do better if we mix the gases in just the right ratio. Now, what's the formula for water? H2O. And this means we have 2 atoms of hydrogen combined with 1 atom of oxygen in every water molecule. So if we wanted the gases to react in just the right proportions, we need to have twice as much hydrogen as oxygen. So before we had equal amounts. This time, we've got 2 parts hydrogen to 1 part oxygen. And this is just the right ratio to get the best bang, or at least we hope so. So again, if you don't like bangs, do put your fingers in your ears. Okay, are you ready? Oh, there we are. Now, just in case you missed that one, I thought, well, we need to try and bring this to the audience a bit more. And, well, what we've done, we've filled this tube that goes all the way around the audience, all the way above your heads. We've filled it full of hydrogen and oxygen gases in just the right ratios to combine, okay? And we have, to stop the gases coming out, we have a bung in this end, and we've got a target to aim it at over here. Okay, and we have a laser-guided bung. Here it is. Now, so far, we've missed the target almost every time. We've hit it, I think, twice. Haven't quite got there yet, so let's just, I think that looks about right. Right, so bung, target. But what you need to watch is the pipe itself. So this is an 80-meter piece of reinforced plastic, okay, filled with hydrogen and oxygen in exactly the right ratios to give us a good bang. Don't look at the target. We'll look at the target later. What you need to look at is the pipe itself. So you need to look above you. Okay, that's where all the action is going to be taking place. So look up at the pipe itself. Now, this happens pretty quickly, this reaction. Blink and you will miss it. So just look up at the pipe, and we'll take the lights down Okay, thank you. And after 5, I will light this, so you just look up, okay? 5, 4, 3, 2, 1. And we've still not quite got there. We've just missed him this time, but almost. Okay, great. So that was hydrogen and oxygen in just the right proportions. What we're going to look at now is another gas that burns, and this gas is a hydrocarbon called propane. And this is the chemical structure of propane. The grey spheres here represent carbon atoms. There are 3 of these in every propane molecule, and there are 8 hydrogen atoms represented by the white spheres. So propane has the chemical formula C3H8, 3 carbons, 8 hydrogens. So this is a hydrocarbon. It contains only hydrogen and carbon, and hydrocarbons burn by combining with the oxygen from the air to form carbon dioxide gas and hydrogen oxide or water, and releases energy, of course. So let's give this a go. So this is propane burning in air. Are you ready? Well, there we are. So the propane there, the hydrocarbon, is reacting with oxygen to form, carbon dioxide and water, releasing energy, but there wasn't much of a bang. So we can probably do better than that, but we need chemistry now to get the biggest bang. So we need to work out what ratio we need to mix the propane gas and the oxygen in to get the best bang. So propane, C3H8, 3 carbons, 8 hydrogens. So let's just pull this apart. Here we are. And we need to work out how many molecules of oxygen we need to combine with 1 molecule of propane. So there are 3 carbons and 8 hydrogens. Well, 1 molecule of oxygen, each molecule of oxygen has 2 oxygen atoms in it. So the formula for oxygen gas that we breathe in is O2, just like the phone company. Okay, equally necessary for life. There we are. So here is the first molecule of oxygen. Now, how many atoms can this combine with? This is just enough oxygen to combine with 4 of the hydrogen atoms to form 2 molecules of water. If we add another molecule of oxygen, well, this is now enough atoms of oxygen to combine with the remaining 4 hydrogens. So we've got 4 molecules of water formed. But we've still got our carbons unreacted. They haven't had any oxygen with them yet. So we need some more oxygen to react with these carbons. So an extra molecule of oxygen here, well, this is just enough oxygen to react with 1 carbon to form a molecule of carbon dioxide. So each carbon dioxide has 2 oxygen atoms in it. So we need a 4th one to combine with this carbon, and in total then we need 5 in order that all of the hydrogens and the carbons can combine to form water and carbon dioxide. So we can summarize this with a chemical equation. So the propane was C3H8, 3 carbons, 8 hydrogens, and we need 5 molecules of oxygen to combine with this to form completely water and carbon dioxide. So that's our chemical equation. Well, let's see if it's correct. So we're going to see if this works. Well, we've seen the propane, pure propane by itself. There was a lot of flames, not much of a bang. This one has propane and oxygen mixed in the ratio 1:1. So let's see what happens with this. So are you ready? So a bit better, but still there's a bit of cloud there, a bit of carbon coming out and a bit of burning balloon. Oops. So still wasn't the best. We can probably do better. So this balloon now has propane and oxygen mixed in the correct ratio, so 1 part propane to 5 parts oxygen. It's the same size balloon, so it's got the same total amount of gas in it, which means actually the amount of propane in it is much less now. So there's much less propane in here. There's 5 parts oxygen. But let's see if it goes with a bit of a bigger bang. It probably will, so if you don't like bangs, I suggest you put your fingers in your ears, okay? Are you ready? Ah. Right. So we've used chemistry there to balance the equation and get the best bang. Now, so far, in all of the reactions that we've looked at, there have all been various things combining with the oxygen gas and giving out energy. But in each case, we've needed to supply some energy to start the reaction. We've needed to either use a match or a candle, a flame, to start the reaction. Now, do we always need to supply some energy to start the reaction? Well, let's go back to our hydrogen. Remember the hydrogen in the bag? We showed that it was hydrogen. We squeezed some out of the bag here and lit it with a match. Well, this time, what I'm going to do is see if we can light it a slightly different way. And I have some metal catalyst here. This is palladium metal, very finely divided palladium metal. I'm going to put a little bit onto this cotton bud and hold this in the jet of hydrogen. So there are no flames, but I'm hoping that the hydrogen will actually light. Well, let's see what happens. Nothing. But keep watching. Squeeze harder, Mark. Ah, there we are. It did indeed catch light. So I can show this. It is burning. The flame is very difficult to see, but I can light a match in the flame that's now burning. There we are. So the hydrogen has caught light with no flames whatsoever. So this is using the very finely divided palladium metal catalyst. Now, catalysts are very important in our lives to help start all sorts of reactions. In fact, your car, if it's a new car, it will contain a catalytic converter. This is the catalytic converter from a car that we've chopped into two, and inside this are, well, there are two parts. These are the catalytic converters themselves. So again, they are very finely divided metals coated onto the surface of this sort of honeycomb center. And this helps any gases that hadn't burnt properly in the car before they come out into the air. It helps make sure that they do burn properly. So if there are any, for instance, carbon monoxide, which is very poisonous, this helps it to burn to form carbon dioxide. Okay, now we can show this with some hydrogen. Now, with this particular catalyst, we do need to sort of warm it up before it works well. So I have a hydrogen jet here. I'm just going to light the hydrogen. It's very difficult to see the hydrogen, but it is now lit. And I'm just going to warm up the catalyst. Now I've switched off the hydrogen. There's no flame. But watch what happens when I put this on the catalyst. So the catalyst is glowing red hot. And it's now lit the hydrogen. So again, no flame, onto the catalyst, glowing red hot, and it lights. Okay, so this catalyst here helps the reaction to take place. What happens? The hydrogen gas sticks onto the surface of the metal. The oxygen gas can stick onto the surface, and so they're coming right next to each other in just the right way to combine. And once they start combining, a lot of energy is released. So that's why you see the catalyst glowing red hot there as this energy is being released, and then eventually it lights the hydrogen itself. Now we have another metal catalyst here. This time it's platinum. And in the flask here we have methanol. It's an alcohol that burns. It's the same alcohol that we started with the coloured flames. We're just going to warm up the catalyst, the metal catalyst, the platinum here, and then lower it into the methanol vapor. And you should see, as this reaction takes place, the catalyst here will begin to glow. This is as the methanol and oxygen are coming into contact with the metal, and they're both beginning to react there, and this will heat up the catalyst, and it should glow red hot, I hope. Oh, there we are. It's beginning to glow, and any second now it will probably light the methanol vapor. There we are. I'll blow out the flame, and the whole process should start again. So again, the methanol vapor is rising over the catalyst, and it will glow red hot as the methanol and the oxygen come into contact with each other on the surface of the catalyst, glowing red hot. That's it. And again, it should light the methanol itself. And then it blows itself out and it keeps repeating, which is really rather nice. Okay, well, we better stop this because we don't want any unwanted flames. So let's just remove the catalyst and Mark can deal with that. So we've seen hydrogen burning in oxygen using the metal catalyst to help start it. We've seen methanol there, again using a metal to start it, a metal catalyst. But some things are so reactive that as soon as they come into contact with air, they burst into flames. And I have two things here. Now the first one is something that Chris has prepared. It's a piece of filter paper, but we've coated it with phosphorus. And phosphorus is a very reactive element, so reactive that as soon as it comes into contact with air, it sets fire to itself. Well, at least that's the theory, and I hope it does. Right, now at the moment, because we can't have the white phosphorus in contact with air, we've filled this container here with a different gas called argon. Argon is incredibly unreactive. It doesn't react with anything at all. Absolutely nothing. So the phosphorus is safe at the moment, but as soon as it comes into contact with the air, it should catch fire. So when I take the filter paper out and hold it up, hopefully you'll see a reaction. If we can just have the lights down just a little bit, please. Thank you. Oops. There we are. So as soon as it came into contact with the air, it burst into flames. Good. So that was phosphorus reacting with air. And here's the chemical equation for this. We have phosphorus combining with the oxygen from the air to form, well, there are various phosphorus oxides that can be formed here, but again, releasing energy in the form of light and heat. Okay, well, we have here another substance that's very, very reactive. Thank you. And this compound contains a metal. It contains lithium metal, and this should give it a flame, a red colour. And it also contains something, well, as soon as it comes into contact with any moisture, it forms methane, and methane is very flammable as well. So this should start all by itself as soon as I take the top off of this. Again, it's stored under argon. Okay, so there we are. The red colour that you saw there was from the lithium that was present. And so the substance reacts with any moisture in the air to form methane. Methane is another hydrocarbon, contains 1 atom of carbon, 4 atoms of hydrogen, and it is flammable. Methane is the gas that we'd normally use most of the time for our cooking. It's the gas that's present in normal natural gas. So I have a handful of gas here, and I hasten to add I am wearing fireproof clothing and should be able to just light this. There we are. So that was methane burning in air, but I needed to supply a light in order to do that. We can see the chemical equation for this. Methane has the chemical formula CH4, and this is combining with oxygen to form carbon dioxide and water and releasing energy. Now, methane, say, is made up of carbon and hydrogen. In the same group of the periodic table as carbon is the element silicon. And silicon has rather different properties. We have the gas silane, which has 1 atom of silicon combined with the 4 atom of hydrogens. This gas is more reactive than the methane that you saw. As soon as this gas comes into contact with air, well, the methane we needed to light, this gas spontaneously catches fire. So I'm going to add some acid to the container here. In the bottom we have a funnel with a compound called magnesium silicide, and as soon as it comes into contact with acid, we get a gas called silane, SiH4. And any second now we should see some bubbles forming. And the bubbles, when they come into contact with the air, I hope, should catch fire, all by themselves. That's it. So this is silane gas. So it's, we should get a few more bubbles coming up. And a few more, there we are, a few more flashes. That's it. Silane, SiH4, so this is silicon now in place of carbon. This gas reacts with oxygen to form water and SiO2, silicon dioxide. So this will carry on, we'll hear some crackles from this throughout the rest of the lecture as these gas bubbles come to the surface. Now, silicon dioxide that's being formed here is also known as sand. And sand is one of the things that we could use to put out fires. So sand could be used, we could also use water, we could also use carbon dioxide. Well, let's just have a look at this. We're going to start a fire now and see if we can put it out using some carbon dioxide. Okay, so here is some petrol. We're going to set light to this. Okay. And use carbon dioxide to put it out. So carbon dioxide is very good at putting out fires. Well, is it good at putting out all fires? Let's have a look. The tank over here is filled with carbon dioxide gas. Now, carbon dioxide is heavier than air. Heavier than air, so this tank is filled with carbon dioxide, and it should put out a fire. So I'm going to put into this some petrol, some cotton wool soaked in petrol set alight, and it should be able to put it out. Okay. So here we are, burning petrol into the carbon dioxide. And it's gone out. Let's try that again. So carbon dioxide is heavier than air, so it's staying in the tank. But as soon as I put the burning petrol in, it goes out. Now, could this be used to put out burning magnesium? Well, let's try it. So I have some magnesium here. And I'm going to set this on fire and see if we can put this out in the carbon dioxide. So here the magnesium is burning, and lower it into the carbon dioxide, and actually it's burning even more vigorously than it did before. And if I put in the burning petrol, it's still put out, but I can't light my petrol on the magnesium. So the petrol will not burn in the carbon dioxide, but the magnesium will. Okay? So carbon dioxide is very good for putting out fires that form carbon dioxide or water, but it's no good at putting out the magnesium. Well, what's happening here? If I reach in and take this out, well, you see a lot of smoke forming on the surface here. This is magnesium oxide. And if we look at what's left, we see some white magnesium oxide, but deep inside here, there's a lot of black, and this black is carbon that's been formed when the magnesium has stolen the oxygen from the carbon dioxide, so forming magnesium oxide and leaving behind carbon. So we can show this with a chemical reaction, a chemical equation here. So this has magnesium reacting with carbon dioxide, so Mg is the magnesium, carbon dioxide reacts together to form magnesium oxide. The magnesium steals the oxygen from the carbon dioxide, leaving behind the black carbon and also releasing energy. So the magnesium burns in the carbon dioxide. So we can't use carbon dioxide to put out burning magnesium. Well, could we use water instead? Right, now we're going to try this. We've got a beaker of boiling water here, and I'm going to light some petrol and put this into the beaker. Well, before it even gets into the bottom of the flask, haven't even put it into the water yet, the steam has put it out. So even the steam puts out the burning petrol. What about burning magnesium? So I need to light the magnesium to get it going. Going to get it going, get it burning. Okay, and lower it into the steam and into the water. And look how vigorous the reaction is. So even in water, the magnesium, well, it burns in water. This is combining with the water, it's stealing the oxygen from the water, forming, again, magnesium oxide and, well, giving out hydrogen. So we can show this with a chemical equation. We have magnesium reacting with water. The magnesium steals the oxygen, forming magnesium oxide, and forms hydrogen gas. What else could we try to put out our burning magnesium? Well, we could try sand. So we're going to see now if we can, if burning magnesium reacts with sand. Sand is silicon dioxide, and in this tube here, I have magnesium powder and silicon dioxide. I have normal sand. And see if this can put it out. What do you expect? Okay, now this takes a little bit of time for the reaction to start, before the magnesium burns. And we're trying to see if burning magnesium reacts with sand. Okay, so I say this will take a little bit of time just to get it hot enough. But once it's hot enough, we want to see if there's any reaction. Okay, so warming it up. It's beginning to go. Okay, there we are. It certainly did react. In fact, half of it's all over my safety screen. So even sand reacts with burning magnesium. Okay, now, what do we get when this reacts? Magnesium and sand. So the magnesium steals the oxygen from the sand or the silicon dioxide and initially forms silicon and magnesium oxide. But the silicon that's formed here can react with more magnesium, and it forms magnesium silicide. Now, this was the substance that we had in the tube here that's still crackling away, forming silane gas as the bubbles come into contact with the air. And we should be able to show this. I'm going to take the test tube that we've just heated up and smash it up. Okay, and then tip this into some acid. Yep, thank you. And we should be able to see some of the crackling that we had before. So if we just have the lights down, please. Okay, again, this is forming silane gas, SiH4, and this, as soon as it comes into contact with air, spontaneously catches fire, as we see there. Okay, now then, very nearly finished. But I just wanted to show that, well, everything that we've seen reacting so far has all had oxygen in it. So all the burning reactions we've had have had oxygen. Do things have to have oxygen in order to burn? Can we burn things without using any oxygen? Well, we can. Now, Chris has filled up this apparatus here with another gas, chlorine. Now, chlorine is very poisonous, so we've had to take precautions here to absorb any chlorine that's coming out through the apparatus here. But I wanted to show a reaction now with no oxygen whatsoever. Now, in this balloon is another gas. It's a hydrocarbon called acetylene. And this burns. I should be able to set fire to this. Okay, it burns. Very smoky flame here. Okay, but I need to start this by putting it into the Bunsen flame to get it to burn. So this is acetylene or ethine. So it's 2 carbon atoms and 2 hydrogen atoms in each molecule of this gas. Now, I'm going to put this into the chlorine. So there's no oxygen at all in this. I'm going to turn the tap any second and watch what happens. There we are. As soon as the gases mix, as soon as the acetylene comes into contact with the chlorine, we instantly get a reaction. It's burning, so there is no oxygen in this reaction. This reaction is just chlorine and acetylene. If we have the lights up, please. So you can see all the carbon that's forming here because the reaction isn't really complete. So it's a very smoky reaction, but nonetheless, this is a reaction involving no oxygen at all. Okay, if we wheel this one away, please, and we'll swap it. So that was a hydrocarbon spontaneously burning in chlorine. Okay, no oxygen at all. We have another flask here. We're going to see if hydrogen can burn in chlorine. Okay, now, the hydrogen needs, this time it doesn't burn all by itself, it needs something to start it, so we're going to use some acetylene, some of the ethine, to start the reaction. So this balloon has the acetylene in, yes? Yes, please, yep. And this balloon has the hydrogen. So I'm going to put the hydrogen balloon into the chlorine. Chris is going to put the ethine or acetylene in. Okay, and well, I just need the nozzles to meet. That's good. So in a minute, I'm going to open mine, and Chris is going to open his. So if you open yours, then Chris. Oops. Try again. Okay, and yours off. There we are. So mine is now burning. Just leave yours there. That's fine. But there is no carbon being formed. It's only from the acetylene there. The hydrogen is burning by itself. We can have that one out, thank you. Okay, good. So the hydrogen burnt in the chlorine, so no oxygen there at all, and the reaction that we saw is hydrogen combining with chlorine. No bang, it was just burning very nicely. Can we get a bang here? Well, we can get a bang if we mix them in just the right ratio. And in a moment, we have a tube here that's filled, not this one, this is an empty one, but this tube, a tube like this, is filled with hydrogen and chlorine. And it's blacked out on the top and the bottom, but not in the middle. And what we're going to do is start this reaction not with a light, but with some light. Okay? Not with a candle, but with some glowing light. We're going to use some magnesium. Okay? So the light from magnesium, as we put it near the open window of this tube, should start the reaction. Okay. Okay, just need to find my magnesium, my tongs, my burner. Can I have the lights down, please? So we don't want it too bright, because otherwise it will start. Okay, so before we just had it gently burning. If we apply if we mix the gases in just the right ratio, we should be able to get a bit of a bang. So I'm not going to put this burning magnesium into it, just going to hold it near the tube. And there we are. We get a nice bang from that. Can I have the top on? Thank you. So we've seen gases burning mainly by combining with oxygen, but it is possible to have gases burning, things burning with other gases. Chlorine is one gas. It's a very reactive gas. So perhaps this would be another way that life forms could exist, not by breathing in oxygen, but by breathing in other gases like chlorine. So we could perhaps get chlorine life forms on different planets. Okay? We can get energy from the reactions of different substances with other gases other than oxygen. Well, that just about finishes the end of the lecture. I hope you've enjoyed it. We've got two more things to show you just before we finish. So coming back to our cotton wool, well, you remember the cotton didn't burn terribly easy to start off with. We needed to supply some pure oxygen in order to get it to burn properly. Well, this time we've got some more cotton wool, and we've chemically modified it. We've built more oxygen into it. So this should burn. So this is, in case you didn't recognize it, it's clearly a Cheshire cat, okay, like from Alice in Wonderland. So this now has cotton wool, but with the oxygen built in. So this is now nitrocellulose. We've nitrated this, and we should be able to see a nice reaction. Okay, and finally then, just in case you missed the hydrogen balloon before, we thought we should finish with a bit of a bang.